This is Daniel Coosbury, and in this video, I'm going to give you an example of how to perform a one-sided hypothesis test for the population proportion that we call little p. So we're interested in estimating the population proportion, and we're labeling it with a little lowercase p. So we have a population, and we're interested in some sort of proportion of this population that falls into some category. And so usually what we mean by p, by proportion, we mean that you take the number of folks in the category, or maybe they're things or people in category, and then you divide that number by the total sample size. So our kind of shorthand way of finding p is x over n. So this is count the number of people in your category and then divide by the total number. And we want to estimate this thing, and we don't know what it is. We don't have all the population data. So what we're going to do is we're going to take a random sample, and from this population, we can't compute p, but we can compute p hat, which is the sample proportion, which is found in the exact same way, where you take the number of people in your category and divide that number by the sample size. And I've made a mistake. So in this case, this would be the population size. This would still represent the number of things in the category. This is your sample size. But they're computed the same way. So you'll use your sample size. And we're going to use this estimate and the properties of p hat to construct a hypothesis test for the population proportion. So this will be fun. We've got a Republican congressional candidate who takes a poll 8 weeks before the election in which 52% of the 1,124 people responded that they would vote for her in this time, 8 weeks before the election. If the election were held today, can we conclude that she'll get elected at an alpha is equal to 0.05 significance level? So we've got to come up with hypotheses about p from this example. And our general hypotheses are going to look like h0 and h1. And the parameter we're hypothesizing about is little p. And h0 always has an equal to. So we need some sort of number here that can be p is equal to some number, whatever that is, some proportion, something between 0 and 1. And if we reject this, then we're going to conclude the other thing. Now, this might be a little hard to just kind of come up with off the fly, but I do know that I can't use this number 52% because this is p hat. I don't ever use the sample statistics when I'm talking about parameters. That's going to come in later. This is n. I can't use that. That has to do with the sample. I want to hypothesize something about p. So I know that she's going to get elected if at least 50% of the vote of the people who vote for her. And so it'd be nice if I put at least 50, or maybe not at least 50, sorry, greater than 50. 50% votes for her. I don't think that's enough. You need greater than 50%. So it'd be nice if I could put greater than 50% on here, but I can't put it here. There's always got to be an equal sign with h0. So how about I do this? I'll put greater than 50% here. Don't get those two numbers confused. Which, by the rules of how this is designed, then I have to put 50 here. So let's just hold on for a second and see what these hypotheses are saying. This is saying that 50% vote for her. And if we reject it, this is saying that more than 50% vote for her. In other words, this is saying she gets elected. This is saying she doesn't get elected, or we don't know. So if we can reject h0 in this case, we're going to say she got elected. But if we can't reject h0, then we can't say she's going to get elected. Of course, this is 8 weeks out. So this is the hypothetical if the election were held today. Our significant level is given to us. It's 0.05. So we want to reject the null hypothesis with a 5% chance or less of being wrong. Let's go on and talk about the test statistic. So we have p hat. We have that p hat is equal to 0.52. And we know that from the central limit theorem that p hat has a normal distribution with the mean p and the standard deviation of this guy right here. And if we find the z-score of this, remember the z-score, you take some value, subtract the mean, divide by the standard deviation. If you take this, subtract the mean, divide by the standard deviation, you get this guy right here. So this is very similar to z is equal to x minus mu over sigma, where the mu is this thing, the sigma is this thing, and that's x. And so if you find this, this is going to be our test statistic that we use to compute. I threw zeros in there to denote what P is under the null hypothesis. So if P is equal to 0.50 under the null hypothesis, this number is also called P naught, not to be confused with peanuts, P naught. So then you have this test statistic, which follows the standard normal distribution, which is really nice. So like the context where we know what sigma is, but we don't know what mu is, we're estimating for mu, we can use standard normal. Here we're going to use the standard normal too, which is really nice. So let's go ahead and find the test statistic. Our p hat is equal to 0.52. This is the proportion of people in the sample that said, yeah, I'll vote for you. Our p naught is our proportion under the null hypothesis. That's 1/2. So remember, we had to set it up so that it was equal to 1/2, and if we reject it, we get greater than 1/2, which is what will get her elected. So that's 1/2. This is also p naught, and that's also p naught. So there's 1/2, there's 1/2, 0.5. And our sample size is 1,124. You find all that in the calculator, you get this positive 1.34 as your test statistic. Excuse me. And you note that this will follow the standard normal distribution. So we're going to now look at the standard normal distribution. Let's start by doing the critical region method first. We don't need to do both of these, but we're going to do both just for the purpose of the video. You only need one to draw a conclusion. So what we're saying with the in order to draw the conclusion, we're saying if this is true, if H naught is true, if the P is really 0.5, is it unusual for a test statistic to be at least as large as 1.34? So we're doing a one-sided test as evidenced by this thing. This is a right tail test. So we want to see is it at least as large as 1.34. So let's go ahead and mark off the upper, the extreme region. So the critical region is going to be the area in the right tail, the right tail whose area is equal to 0.05. So if Z falls in this region, we're going to call it unusual. And if it's not in the region, we're going to say it's not unusual. So what I'm doing is I'm subdividing this standard normal distribution where I'm going to find some value that'll separate the lower 95% from the upper 5%. And I'm going to say that if Z falls in here, then it is going to be unusual. If it doesn't, it's not unusual. So if Z falls in here, we'll reject H naught. If it doesn't, we won't reject H naught. So I need to find this guy. This guy, Z sub 0.05, we're going to find using inverse norm because we're in standard normal. The area to the left is 0.95, the mean is 0, and the standard deviation is 1. So you can do that in the calculator and get that value. So I'm going to do inverse norm. Area to the left is 0.95, the mean is 0, standard deviation is 1, and I get 1.64 or 1.645 if you're getting that from the table. So the value I get is, this is 1.645, and that marks off this region here. So anything bigger than 1.645 is going to be in the critical region. Anything smaller than 1.645 is not in the critical region. And look, our test statistic is smaller than 1.645. So on my picture, it would go right around here. So this is 1.34, which is Z. In other words, it's not in the critical region. So if we said if it does fall on the upper 5%, the extreme things, we'll call it unusual. Since it doesn't fall on that upper extreme tail, we're not going to call it unusual. In other words, we're going to say that since Z does not fall in the critical region, the probability of its occurrence is greater than 5%. So it falls in anything in here is under 5% chance of happening. This is a greater than 5% chance of happening. So we're going to conclude it's not unusual to get this statistic if P is really 1/2. So if the null hypothesis is true, this is not unusual. So that's our conclusion. We're going to fail to reject H naught because this is not unusual. It doesn't fall in the critical region. So if you want a nice hard and fast rule, since this is not in the critical region, you're going to fail to reject H naught. Those always go together. If it's not in the region, it's not in the critical region, you don't reject H naught. So what does that mean? H naught said that the mean is 1/2. I'm sorry, not the mean. P is 1/2. And H1 said that if we reject H naught, I'm sorry, I'm doing something a little off. H1 said that if we reject H naught, P is going to be bigger than 1/2, and we couldn't conclude H1, so we're going to have to stay here and say, well, I don't think this is wrong. This is probably fine. We do not have sufficient evidence to reject H naught and conclude the proportion of voters who will vote for the Republican candidate is greater than 0.5. That is, if the election were held today, we do not have sufficient evidence to conclude she'll be elected. So this is really important because if you release poll results, and even if it's close to the election, which might matter even more, if you release poll results that say, hey, 52% are going to vote for me, statistically speaking, that's not high enough with that sample size to say that you're going to win. Because our hypothesis said that, anyway, what we're concluding is there's not evidence that the proportion of people who are going to vote for you is bigger than 50%. We can't say that for sure. So you got to be careful in how you read poll results, because 52% you might think, oh, well, it's in the bag, and that's just not necessarily true. Let's look at the p-value method for this as well. So the p-value method, we want to see how unusually large, how large is this unusually large? So what's the chance of getting a test statistic that is bigger than or equal to 1.34? What's the chance of getting something here? Now notice this region is a little bit different than the one I found earlier. The one I found earlier started at 1.645 and Z was over here. Now I'm finding the region that starts at Z and goes all the way there. And I want to see, is this unusually high or not? What's the area of this, which is what's called the p-value. So the p-value is the same thing as the area of this red region that I just shaded, which is the probability that Z is at least as big as 1.34. So all these things mean the same thing. This area, this probability, and the p-value, they should all be the same number. And I'm going to find that using normal CDF. So normal CDF, I'm going to start at 1.34. I'm going to go all the way to 9999, and I'm going to use the standard normal distribution to do that. So I'm going to do normal CDF. Start at 1.34. Go all the way to some big positive number. Mean 0, standard deviation is 1. And I get 0.0901 as my p-value. My p-value is 0.0901. So that's the area of this thing. So you can kind of see on the picture, it's almost 10% of this distribution. Almost 10%. It's 9.01%. Now what does that mean? Well, we found the p-value is 0.0901, which is greater than alpha. So what we're saying by this number is if our null hypothesis is true, if p is really 1/2, then the probability we take a sample with the proportion at least as large as 0.52 is 0.0901, which we're calling this not unusual. See, what makes it unusual is if it's less than 5% chance of happening. This is a 9.01% chance of happening, which is not unusual. So we're going to fail to reject H naught because our results have a 9.01 chance of occurring if H naught's true. You could also say we're going to fail to reject H naught because our results are not unusual. The chance of them happening is not less than 0.05. So they're not unusual. So we'll conclude the same thing. We don't have sufficient evidence to reject H naught. We can't conclude that she's going to be elected just from this one poll if the election were held today. So that's how a one-sided test for the proportion works.